So this year I'm going to start from the beginning. Okay, yeah. So I may add some new materials into this course, okay, but that's my best, as long as the computer cooperates with me. So you learned vectors in several courses, and in first year linear algebra you also learned here. So we're going to quickly go over this concept here. Okay, yeah, so it should be quick. First of all, very simple concept. What is a vector, and what characterizes a vector? Okay. When you talk a vector, okay, everybody knows it's a line with an arrow. Okay. Now, more precisely, okay, what we see is vector has two things. One is direction. Okay. The other is magnitude, or we call it length. Okay. Direction, which direction the arrow points to. Magnitude, how long that arrow is. Okay, that defines a vector. Is that clear? Okay. So often in time, okay, if I use wording, I just say, okay, if this is this one, so basically we see it's a length. Length is a scalar quantity, right? 3 or 2 or 5. But direction is not a scalar quantity here. So length times the direction. Okay, that gives you the vector. So as you're going to see shortly, direction, we're going to use a so-called unit vector to represent the direction here. Okay, yeah, but every vector contains this format here. So now I'll ask you a very quick question here. So this is the coordinate system we're going to use in 3D space, x, y, z. Okay. So you probably you see I will draw a vector. Okay. Starting at here, and then I'm going to draw another vector. Okay, and that vector, I will draw it at here. But, okay, in your words, that vector will have the same direction and the same length. But I draw it at here now. Okay? So let's say this is a vector A, and this is a vector B. So here's a question. Okay, remember what I said? This vector B has the same length and same direction as A, okay? But different location though. Are A and B the same vector or different vector? How many would say same? It's not a majority. How many would say no? Or, yeah, not a majority, so the others are not decided yet. Definition. What characterizes the vector? Direction and magnitude. What did I just say? B has the same direction and magnitude. So B and A actually are the same vector. Okay? So here brings the concept here. Vector is free. Free meaning what? Free means it's not you rotate it. It's free to move parallelly, okay, to anywhere in a 3D space. Okay, so that's what we mean by free. Parallel. Okay. Yeah. So that's a simple concept. Actually, I find that often in time it's a little bit hard to, because you say, oh, that's at a different location now, right? But it's free. If you move this B back here, right, it will coincide with the A. Okay, that's basically what it means in here. Okay, so next thing is, in this course, you will get used to some of the notations or some of the styles I write for vector for other things. So when I write a vector, okay, we generally will deal with a vector in 3D space. So we're going to use this symbol here, this half bracket, to indicate a vector, basically we write it like this. Okay. So I use a half bracket for angle bracket for vector, and A1, A2, A3 are the vector components. Okay. Yeah. Now you also have this concept called coordinates, right? Coordinates. So when I write coordinates, so here's a concept here. This is the coordinate system. If we let this point, let's say this is a point P, right? This is point P here. Then apparently OP, okay, as you can see now, that OP is basically the vector A at here, right? It's the vector A. Okay. Now, if it's a vector, we say we use this notation, but the point P is a point. So the coordinate for point P for this point P is what? We use this symbol now. Okay, so it's this. You see that? Yeah. Would that be okay? Yeah. So bracket. Okay, when we write coordinates, I'll use bracket. Okay, but here actually there's a very subtle difference that here. You might wonder, so why P coordinates and vector? What's the difference between these two, right? There is a subtle difference. See, when you write OP, so for the origin O, what is the coordinates for origin O? 0, 0, 0, right? Yeah. So here's basically what you learned in the past. When you're given coordinates of 2 points and being asked to write down the vector from one point to the other, for example, like OP. So basically, what does that mean? That means it's the coordinates of what? Of point P subtracting coordinates of point O. So it's always the coordinates of the second point subtract the first one. So basically that means this is A1 minus 0 and A2 minus 0 and A3 minus 0, right? Yeah. So that's where that vector A1, A2, A3 come from. Okay. Yeah. So get used to this idea here. Okay. If more general, if point P is x1, x2, x3, point O is y1, y2, y3, that kind of information, just do the subtraction, right? Yeah, the subtraction. Now the next one is, what will be the length? So how do you calculate the length of a vector? So this is pretty simple. Here's a vector. So what will be the length of the vector? So the length of the vector, what we do is, I'm going to use this symbol here to represent the length. In some textbook, they use doubled lines, okay, to represent the length. But I'll just see myself writing with 2 vertical lines. I'll just use this one here, okay? Use this. Okay. And the other thing is, I have A, there is an arrow on the top of the A to represent that as the vector, okay? But in most of the textbook, what you see is a bold letter indicating it's a vector, right? Yeah, but when I write here, I can write the bold. So this is basically the reason, okay? Yeah. Now, we know that the length is basically summation of the squares and then taking the square root. Okay, that's the length. Okay. Now back to the simple concept direction. Okay, direction. So when we said there's a length, there's a direction. So what would be the direction? I said I use a univector to represent the direction. Because you see, when I'm pointing to that direction, a vector, I can have a vector of this much length, I can have a vector of this much length, and they all point into the same direction here, right? So to simplify it, so we're going to use a univector. So that's this A hat, okay, representing as a univector here. So what does univector mean? Univector basically means it's a vector having a length of 1. Okay? Yeah, that's basically what it means. Okay, length of 1. So then, how would you create a univector? Okay, how would you create a univector? So what you do is, here is your original vector. Then what do? You normalize that. You divide it by its length. Okay, divide it by its length. So that'll give you a univector. Okay, is that good? So now back to this. The concept vector has a direction, has a magnitude, and the length. And I say vector equal to the length times the direction. So if my vector A is this, then I can rewrite. Okay, I can rewrite my vector A as the length times the direction, right? Times direction. Okay. Yeah, it seems redundant, but because why do you plug it here back to the A, right? But that's the idea. Okay, that's the idea. All good? Okay. So that's the vector here. Review of vectors, right? Yeah. And in your past courses, you must have learned how to add vectors, how to subtract vectors. So I'll skip that portion there. Okay. Okay, let's jump ahead a little bit. So let's look at some of the operations of vector. Two very commonly seen ones, which we use quite a lot. One is the vector dot product. Okay, and the other one will be the cross product. Okay. So first, let's look at the dot product. Dot product basically given two vectors. Let's see, one is A and B vector. Okay, so given two vectors, and we're going to carry out this so-called dot product. Sometimes we call it inner product or scalar product. Then A dot B. So write a solid points at here. Okay. The definition is this. Okay. Yeah. In short, it's this. If I expand it out, this symbol here is called summation symbol. Okay, summation symbol. It starts with I equal to 1 up to I equal to 3. Okay. So if I expand it out, basically it's A1 times B1 plus A2 times B2 and A3 times B3. Okay, that's the dot product. Yeah. A very simple application of dot product here is this. Let's say you want to know what is the length of the vector, right? So what do? So look at that. If you do a dot product of itself, so what do you get? You basically get A1 squared plus A2 squared plus A3 squared, right? Yeah. So if I take a square root of this, I guess what do I get? I get the length, right? Get the length. Okay. Yeah. So the other trivial things is if you have some mathematical background, probably, particularly if you use a MATLAB, you will see that there are two ways of writing a vector. Okay. Yeah. One way is called to write a vector in a row, so that's called a row vector, and let's write a vector in the column. That's called a column vector. Okay. Yeah. So in this course, we're gonna always write a row vector here, but in some cases you got to be careful of that definition, right? Yeah. Okay. So any questions out of here? All good? Okay. So dot product. Next thing is related to dot product is the geometrical meaning. This is what being used quite a lot. You have two vectors. And B at here, let's say A at here, with an angle theta apart. Then if you wanted to carry out the dot product. Okay. So one way is use the hard formula as we just presented it here to calculate the dot product, and the other is here is this alternative formula. Okay, use this. Right, is this. Okay, so A dot B equal to absolute value of A vector plus x multiplied by V and multiplied by cosine theta, and the theta angle, okay, supposed to be, okay, within 0 and pi. Okay, yeah. So I think that's one thing I forgot to mention, emphasize it here now. The end results of a dot product give you what? It give you scalar value. Okay, remember this because this is different from the cross. It gives you a scalar. Basically, it's not a vector anymore. Okay? It's a scalar. So I would recommend you memorize this. Okay, so the other way is often is if you know A, if you know B. The alternate question is what's the theta between the two vectors, right? So then you can, from this formula, it's pretty simple. The theta equal to what? It's the arc cosine of A dot B over A's norm and B's norm, so the lengths, okay, right? So A dot B can be calculated using this hard formula here, and then absolute value absolute B can also calculate easily. And then take our cosine, you get the theta angle. Okay, yeah, let's see that. The important side here is often is this. You see, many times what we're also interested is what is the geometrical relationship between this A and B? Are they perpendicular to each other or not, right? So essentially, there's always a very important thing is A perpendicular to B, right? So how do we determine that relationship? And one of the easy solution can be observed from this formula. When A perpendicular to B, or sometimes we also see that A is orthogonal to B, particularly in 3D space, that means the theta equal to what? 90 degree. If the theta is 90 degree, what is the cosine 90? 0, right? It's 0. So that basically means if this A dot B equal to 0, okay, given the two non-zero, for example, A and B are two non-zero vectors. If this dot product is 0, so that means A is perpendicular to B, okay? Or I sometimes call it orthogonal. Yeah. That's one of the major application of this geometric formula right here. Okay. The other is just checking: is it a dull angle? Is it a acute angle? So that kind of things. Okay. Yeah. All good. Okay. So the next application of a dot product we'll look at is a projection. Okay, projection here. Okay, yeah. So projection, one thing that often arises. So let's say you study dynamics, and then you wanted to know is, okay, so the car is over here is traveling at a certain speed or along this curve right here. Then what is the acceleration at that point, right? The acceleration tangent to this curve and the perpendicular, basically the components of the acceleration of that. So we often write, acceleration tangent to that and acceleration perpendicular to that. So that's the information you probably want to present in that kind of a graph there. Okay. So how do we do that? We use the projection to find the information. Okay. So here's what happens. Now projection can happen in any direction, right? So this is A at here, okay, and this is a B at here, okay. This is a B at here, and we're interested in is I want to find out what is the projection of the A in the direction in the direction of vector b. So we project this A to the B direction. Projection meaning strictly, right, perpendicular to that direction. So that's why I draw a perpendicular line at here. Okay, that's the projection we're talking about here. Okay. So writing in mathematics, for that direction here, okay, for this one here, we're going to use A, okay, parallel, okay, as a symbol for that one. Okay. Essentially, how do we find this A parallel? In the words, we call that projection. Okay, projection of A in the B direction. Okay, B direction. You see, I'm saying the wording in the B direction. So when I say in the B direction, actually I don't need to write this B vector. According to what I just said, I can write as what? B hat. Exactly. Right? So when we talk about direction, we can use the unit vector to indicate that. Okay? Yeah. Of course, you know, this is okay. That's also pointing to a direction, right? Yeah. Okay. So let's look at derive just a simple formula here in terms of direction. So here's what happens, right? Back to the simple concept. Vector, we're trying to find this vector. That vector needs to have two properties. One is direction, the other is length, right? Is the length. So let's assume this is theta here. Direction, what direction is it? This direction, which is B hat, right? This is B hat. So it has a direction. That's a direction. What do we multiply? We multiply with the length at here. Okay? So how do I find the length? The length is which portion? It's this, right? It's this. Okay? So use the geometry. How do I find the length? Length is a scalar, right? It's a scalar. How do I find the length at here? Use the high school geometry. This is right angle. So this length equal to which length? This length times cos theta, right? And this length is what? This guy here, right? It's this. So basically that means we have this length times cosine theta. And that's the length of A parallel. And that's the direction of A parallel. So mathematically, that gives you this A parallel. Okay? Yeah. So then you probably wonder, oh boy, there's so many things mixed up together, right? There's theta A, B hat. Let's maybe expand the information to be more specific. And what we can do is, right, we can use all the formulas we just had. Cosine theta, what does cosine theta equal to? Cosine theta equal to this guy divided by this guy here, right? Yeah. Okay? Yeah. That's cosine theta. And what does B hat? Where's the B hat from again? How do we get B hat when giving a vector B? B divided by? Exactly. Right? Normalize it. So that's all the information based on A and B. So then you can simplify this, cancel some things out of here. So what can we cancel? This A and this A, these two can cancel. Make sense? Right? These two. They're two magnitude basically. They are two values. So they will be cancelled. So we end up with, I don't think you can cancel anything else now. So end up with this guy here. So bottom line is, you have this A dot B, and on the denominator there are two absolute value of B vectors. So that basically will give you what? B squared, right here. And at the top there you have the B vector again, so you can leave it over here. Okay. So that's sort of the you can call it simplification or not, but that kind of illustrates ideas here. Okay, how would you find the projection? Okay, so good. And by the way, is this new? No, right? Yeah, good. So now the next question is, I said I want to find not just the projection, I probably also need the components. So then basically, what will be the components of the A vector in this direction, which is perpendicular to this A parallel. So let's call that A perpendicular, right? A perpendicular. So that's something else we need to find out. If you need that information, okay, so what do? You actually can make use of what you just found from here. So the A perpendicular equal to what? Exactly, excellent. So A vector minus the A parallel, right? Because this is A parallel here. If you move this A parallel up to here, you have this triangle here, head to tail, right? So that basically gives you A perpendicular. Okay. The reason I'm going over this is because we're going to learn lines and planes in 3D space. You're required to find lines or planes equation. So the number one step is often to find some vectors related to the line or planes based on given information. So many of these projection ideas or subtractions, based on the components, you will need to carry out that calculation in here. Okay. Any questions? Okay. Yeah. In the lecture notes, I incorporated some maple commands and the method commands for you to exercise. Okay, so you can play with them and get some more feelings on this thing here. Okay, so next thing is cross product. Okay, so cross product, essentially what we're saying is we have two vectors. Okay, we got two vectors. Okay, so in this case I'll call it A and B. Okay, and we're looking for this thing here called A, like a times B, but it's not a product because this is a vector, not a scalar, so that's why we call it cross product. Okay, so this thing here, not just time, is a cross product. Okay, so the definition is, this A times B, okay, equal to A B sine theta times n hat. Okay, theta is the angle between the two vectors. So this is the definition. Okay, so definition means we don't argue with it. It's people define that, right? Yeah. So we don't need to prove anything. Okay, so it's definition. So what does that mean? You look at this one here. That means actually times n hat. So n hat here is it's a vector, univector, okay, perpendicular, okay, to the plane formed by vector A and the vector B. All right. So this n hat, it's a univector perpendicular to the plane formed by vector A and the vector B. Okay. Two vectors or two lines. Okay. Basically, if A and B are not coincide with each other, you will have a single plane decided. Okay, that's n hat. Then you look at the inside bracket here. This is absolute value of A, absolute value of B, and then sine theta. So the three things that are here, they're all scalar, right? They're all scalar. So the bracket here basically representing certain scalar value. So that basically means what? This is the length times the direction. Okay. So the A cross B basically means end up with another vector, and this vector is perpendicular to the plane formed by A and B. So then, which means you can draw another vector at here, right? That's A cross B. Okay, that's A cross B. Now, not only the that A cross B is this, you might wonder, oh, does A cross B go to the other direction? Maybe the other direction also perpendicular to the plane, right? But you have to make sure that it satisfies the so-called right-hand rule. For right-hand rule, meaning curve your finger from A to B. Okay, the thumb is the direction of A cross B. Okay, or this is A, this is B, then the thumb is direction of cross product. Okay, yeah. So vector, meaning cross product give us a vector. That's the fundamental difference with the product. The dot product give us a scalar, right? Give us a scalar here. So what happens is if A and B are parallel to each other? Pardon me? Sine 0. So that means A cross B will equal to 0. So there's no vector, right? There's no vector. So some website has animations. Basically, when the angle changes, you will see the vector length changes. Okay. So when they are parallel or basically all coincide with each other, then the length goes to 0 and nothing, right? Okay. That's something you need to know there. Okay. So the next question is, how do I find the n hat? Okay, how do we find n hat? The n hat, we said the n hat is the direction perpendicular to this plane, and that basically is the same direction of A cross B. So we can use our old trick to calculate this n hat like this. Okay, so if we have this value of A cross B, this vector here, so then we can just divide it by its length, and that'll give us the n hat, right? We get n hat. Okay, so now you probably think is, how do I get this A cross B then, right? So this is not the only formula you have it here. For cross product, you have the second formula here. So A cross B, you have another formula here. All right? Yeah. Now, for this formula, before I write down the formula, and then I have to introduce another notation I use in this course set here. Okay. So I'm gonna let A equal to A1, A2, A3. That's the vector. Okay. So I'll write another set of notation here. So we write A I1 hat plus A2 G1 hat, no, not G1, sorry, just call it I hat, G hat, and plus A3 and K hat. Okay. So this is something you will see in the lecture notes or in my writing here to indicate a vector. So what is I hat, G hat, K hat? That's what? That's the unit vector, okay, for x, y, and z, okay, axis, okay, yeah. So B equal to B1, B2, and B3. Okay, so then this is the formula. If you want to prove it, actually we do have proof, but I'll just write it down it here. The cross product of A and B is this. So I, J, K, A1, A2, A3, B1, B2, B3. So it's the determinant of a 3 by 3 matrix. The first row of the matrix is the unit vector I, J, K. So they're not scalar quantity, okay? Yeah, they're actually certain quantity here, but it's a vector though, huh? Yeah. Second row is A vector, and third row is the B vector, a component B vector. So then determinant, right? Determinant. You learn linear algebra, 3 by 3. Determine a 3 by 3 matrix is as far as you wanted to go to memorize. 2 by 2 is pretty simple, right? So But I do need you to be able to memorize this though, huh? Yeah. In the past, actually you're the first batch of students who took linear algebra in the first year. In the old time, linear algebra is not established. Okay, we usually have to review something here. So test yourself. Can you write down this determinant at here? So you do an expansion. Okay, do an expansion of the first row. Okay, along the first row here. Okay. So what do we end up with? So cross this out. The determinant of this. I'll just write it here. A2 B3 minus A3 B2 I hat. Okay, I hat. And the second one here. Yeah, the second one is often a mistake that you could make. It's a negative and here. Okay. So cross this A1 B3 A3 B1 J hat. So, but you have a negative here. Okay, you have a negative. And the last one is plus. So A1 B2 minus A2 B1 K hat. Okay. Yeah, so that's cross product. So good? Yeah. Memorize. Okay. There's not going to be a formula for this, right? Yeah, no formula sheets. So you will need this quite a bit. Okay. Okay, so can you practice this quickly? This is A, this is B. What is A cross B? I'll give you 1 minute. Okay, you should be able to finish in 1 minute. Okay. Time's up. What do you get? Do you get this? Yeah? Yeah, good. Okay. Those are pretty trivial, simple things here. Just calculation, right? But I can't emphasize more because often in time, the problem of the course is, in the future calculation, your first step is probably calculate cross product. Guess what? If you cross product, often many people probably put a positive here or something, right? If you do that wrong, the whole process for the rest of the question will be wrong, right? Yeah. So I need you to be careful, be rigorous in your calculation. Okay, so that should be enough for the review. Any questions? So good. All right. So let's take a look at the next one here. A little bit of application. Let's look at the area of a parallelogram. Okay, the area of a parallelogram. Parallelogram meaning it's this one here. Okay, that's a parallelogram. Okay. Let's say this is A, and this is a B. Okay, this is B. So we're looking for the area of this. So it'll end up with something to do with dot product, cross product. Okay, yeah. Now let's look at this one here. Let's start from scratch. Very simple one here. So what do we mean by area? Forget about A and B. If this is a parallelogram, geometrically, when you calculate the area, meaning you use what? The length of the bottom times what? Times height, right? Times height. So basically, length of bottom times height. Okay, yeah. So then that's getting closer to the given information. What is the length of the bottom? It's the length of this vector, right? This vector. So that's what we see. This is my symbol here. That's the length of the vector. And what is the height here? It's h, right? It's h. So let's say the two vectors are having a theta apart. Okay. Then scalar value h can be obtained based on the length of b and theta, right? Yeah. So what do we get? We get the length of b times sine theta. Okay, times sine theta. So now you look at this one here. What does that remind you? A magnitude times b magnitude times sine theta. What do we see? We see this quantity here, right? See that? Yeah. And that quantity represents what? It's the length of the cross product. So basically, I can rewrite that as this is the length of the cross product. Okay, cross product. Okay, so which means the area parallelogram formed by two vectors separated by a theta angle. The magnitude is the length of the cross product, A cross B. Okay, yeah. And more interestingly, okay, a little bit if A and B, okay, are 2D vector, okay, there's only 2D vectors. 2D vector basically means the z component is 0, right, for the A and B at here. Okay, yeah. So maybe A is A1, A2, and the B is okay B1 and B2. Well, you can put a 0 here if you want. Okay, yeah. So then for this particular case, if we want to find the area formed by the area parallelogram formed by A and B, so I'm going to plug it into this formula that we just find it out, right? So let's see, what do we have here? So the area equal to absolute value of A cross B, because area is a positive value. Okay, yeah. A cross B, we have the formula, right? You know, the determinant of the 3×3 matrix. Okay. So what do? You basically plug into the formula I, J, K, and A, A1, A2, 0, B1, B2, 0. Okay, yeah. So nothing tricky, just plug it in and do the calculation. Okay, do the calculation. Because it's 0, 0 right here, and you'll find out this is equal to A1, B2 subtract A2, B1. You'll find it this. Okay. Basically, it's this times this minus this times this. Okay, and this. Okay, yeah. That for this purpose, we actually we can introduce this. If we say for this one here, we can call that's the absolute value of determinant. Okay, A B. Okay, determinant A B. So what does that mean? Basically, when we say determinant of A, B, okay, it's this A1, A2, B1, B2. Okay, yeah, the symbol there, right? So that basically match this thing here. So determine this. That only applies to the 2D case though. Okay, yeah, because I need this similarity for the next application. Okay? You'll see that. It's all good. Okay, so now let's look at the next application. Volume of a parallelepiped. Okay. Volume of a parallelepiped. What we mean is basically, I'll draw it here. Given three vectors, okay, given three vectors A, B, C. So let's see, this is a B vector at here, and this is a C vector, and this is A vector. Okay. Three vectors. So the three vectors are in 3D space. Have a little bit 3D sense, so they are sort of separated by certain angles pointing to different directions. And then we're going to form this parallelepiped based on the three vectors. First, form the base using the two vector B and C. Then we form this parallelepiped using the vector A. Okay. By keeping necessary things to be parallel. Okay. So that's the parallelepiped. Okay? Yeah. And we're looking for the volume of this thing here. Let's just say A is A1, A2, A3. And B is B1, B2, B3. And C is C1, C2, C3. Right? Okay? Yeah. Okay. So before we move on, okay, let's do very similar steps as we did in the previous application. Okay, volume. Okay. So giving you a geometry, 3D geometry like this. So volume equal to what? The base area times height. Okay? Yeah, right? Nice good stuff. So height basically means the vertical difference between the top surface and the bottom surface, which are parallel, right? Yeah. So we can draw a vertical lines up from this point to perpendicularly, okay, to the bottom surface, okay, as that height. Okay, so let's see, this is the height at here, right? Is that good? Yeah. Suppose that the angle between B and C is theta, okay, given this symbol right here. Okay, you may or may not need that. Okay, so now let's plug in the information at here according to this base area times height. Okay. First of all, what is the base area? Parallelogram. Did we just find it out? Area of a parallelogram. So what do we use? We use what? This thing here, right? This thing here. Okay. So it's B cross C. Okay, absolute value. Okay, that's the base area. Height. So height is this h here, right? It's h. Now you need to think in terms of the concept of the projection. Okay, projection. When we review the dot product, it's one of the major applications for dot product is to see the projection, right? The projection. So if you look at this, if you look at the dot product here, Okay, right here, right? So for example, what is the length of this portion here, right? The length of this portion is projection A in the direction of B at here. Okay? So you see, this A parallel is the length times the direction, right? Times the direction. Then the absolute value will give you the length. Okay? Will give you the length. Okay? So in this particular case, let's come back over here. Okay? Come back here. Where's my length? We're talking the length here. And that length is actually what? The projection of A in which direction? In which direction? Go ahead.
On the normal vector of the BC plane?
Exactly. Right? If you project this A, this H here is perpendicular to this bottom plane here, right? Bottom plane. And we learned in the cross product, you know, every plane, if you draw a perpendicular direction, let's see if I draw a perpendicular, I need to the red color here. So let's see if I draw a vector that is perpendicular, okay, to this plane. Is that okay, right? Yeah. Then the H can be found by projecting this A into this direction indicated by this vertical vector. Does that make sense? Yeah. So let's find the information one by one in here. First of all, you got to construct this vertical vector first, right? To have this vertical vector. So how do we get that vertical vector though? It's B cross C. So this one here, a handy candidate for that vector is a B cross C, right? It's B cross C. Okay. This is a vector, huh? This is a vector. It's not a direction yet. It's a vector. But what we want is we want to have the A projecting to the direction indicated by B cross C. So I use a shorter symbol n hat to indicate the direction pointed by the B cross C. Okay? Yeah. And then what we need is we need the projection of A to that direction, right? To that direction. So all you need is A vector dot n hat. Okay? Dot n hat. So A dot n hat will give you dot product. First of dot product give you what? A scalar quantity, right? Scalar quantity. Okay? And A dot n will give you this H at here. Okay? Will give you the H. That make sense? Yeah. It's getting to 5 o'clock. I know the brain is not functioning as morning, but that'll give you the H at here. Okay? Yeah. So the next question is how do I get n hat though? N hat equal to what? B cross C divided by B cross C. Right? Yeah. So plug this into this bracket here. Okay? Plug that into the bracket. So let's see, what do we have? You will see that you have this B cross C absolute value here. You have the B cross C here on the denominator, so they actually will cancel each other, right? Will cancel each other. So you end up with what? Just A dot B cross C. Okay? You end up with this simple here. Okay? Now, in this case here, there's another name. Sometimes we call this is a triple scalar product. Okay, triple scalar product. As a matter of fact, if you look at it carefully here, okay, so you're calculating the volume with the base area times this height. or maybe I can use this base area times the height, right? Use another area times the height. So in that case, you will end up with a slightly different order. Okay, you will end up with this. Maybe C dot A cross B. Okay, like this. So they're all the same thing though. Okay, or you probably will be B dot A cross C. Okay. And more interestingly, this is the last point I want to illustrate it here. You will find out that this I'll use this A dot B cross C. Okay, you'll find out it's actually equal to determinant of A, B, C. Okay, absolute value. I probably should have put it that abs, but let's put it here. Okay, so what does that mean? Determinant A, B, C basically means A1, A2, A3, B1, B2, B3, and C1, C2, C3. Okay. Yeah. So volume of a parallelepiped equal to the determinant of this 3 by 3 matrix. Okay. Yeah. And we all know how to calculate determinant of this, right? So that's a nice connection between the area determinant of this. Okay. Any questions? Okay. We're good. Okay. Thanks.